Okay. Well,
wait a sec, there is someone unmuted, I think.
sure.
Saying something. Yeah, okay. So everyone except Tom is muted, I hope. Yeah.
Okay, so I'm not muted, I hope. Right, so I have the chat open, so if you have questions, you can write them or ask them anytime. I think that's the best part of a seminar. Okay, so this is supposed to be our cellular, motivic, invariants, let's say of Z1/2. Okay, so this is, well, I think it's a nifty little result. Maybe you will be the judge if it's nifty. So this is joined with Paul Arne, joined with Paul Arne Østvær at Oslo. Okay, so I'll begin with a few recollections before I can state the main result. I guess it's a part of the trouble of this business of motivic homotopy theory that you always have to introduce a bit of background. All right, so what do? Well, there's this sort of motivic thing in my title, so I should at least pretend that we know what that means. So S is going to be a scheme. But I mean, the most relevant schemes today are going to be just spectra of some well-known rings, like, well, the integers and the finite fields and so on. So don't be too afraid of the scheme. And then you have this category, which is called the motivic stable category. And well, I mean, I can give you a one-line definition, but it doesn't really matter, except that then it's clear sort of that you can take a scheme and yes, let me write the one-line definition, which is that you take pre-sheaves on smooth schemes, you perform some localization, you look at pointed objects, and then you monoidally invert some other object. Doesn't really matter, but I mean, particularly if you take any smooth S scheme, you can sort of move it into this category, and this is somehow a more fancy version of schemes in some sense. Okay, and you already see that, as indicated, this thing depends on your scheme, right? And so you can, if you change the scheme, you get a functor. So if you have some morphism of schemes, then you get an induced functor, which is called base change, f up a star, and it goes, well, the other direction as the star suggests, like this. And actually, this guy always has a right adjoint, which is called a lower star. All right, so what else do we do? Well, the objects, they're called motivic spectra. And if I have two of them, then there's going to be a set of maps, of course, between them. It's actually a space. And in fact, because this is a stable category, there's actually a spectrum of maps between them. So you have this sort of mapping spectrum from E to F. And this is going to be a spectrum in the usual sense. What else do we need? Okay, so this is a symmetric monoidal category. And in particular, there's the unit, which is the unit. So I'm going to write the unit, well, I'm going to write one for the unit. And sometimes maybe if it's not clear, then I'm going to write 1s to make it clear which my base scheme is. Okay, what else do we want? Yeah, so what we do, then we combine all of these things here in the following sort of notation. If E is one of your motivic spectra, and if X is any S scheme, not necessarily smooth, then what I do is I write E of X, and this is going to be a spectrum in the usual sense. Name is going to be maps from 1x into P upper star E, where P from X to S is the canonical map, right? So it just means that if you have one of these motivic spectra, you can sort of evaluate any scheme on it and you get out a spectrum. So you build yourself a pre-sheaf of spectra. And we think of this as sort of like the the spectrum valued cohomology theory represented by E. What else do we do? Right. So you have.
Sorry, can I just to clarify? So if X is actually smooth over S, is this then this maps in SH from X into E?
I mean, the way I've written it, this is maps in SH of X.
Huh?
But you're right. If X is smooth, then there's a P lower sharp, and you can then move this to the other side, and then it's mapped sort of from X to E. That's right.
Thanks.
Sure. Okay, so now in classical stable homotopy theory, you have like the sphere spectrum and the spheres, and they're very important. And similarly, in motivic homotopy theory, we have the spheres, but actually, again, it's not going to be a surprise for anyone. You have these bigraded spheres. So I'm going to need a little bit of notation maybe for those bigraded spheres. And I'm just going to say that you obtain them by applying this bigraded suspension to the unit. So this is going to be some specific motivic spectrum. And namely, what is this bigraded suspension thing? It's, I guess it's, you use the usual suspension, P minus Q times, and then you take sigma infinity of the affine line minus the origin, and you point this by 1. So now you have a pointed space. And then this guy turns out to be invertible in this category. And so I can tensor it up as many times as I want for any integer, and the number that you take is Q. So this is just some fancy notation for doing this, right? I mean, it turns out that there are sort of two canonical invertible objects in this category. One is the usual sphere, and one is maybe this guy. And then this is just some linear combination of them, which happens to be convenient. Okay, and now one thing is that in classical homotopy theory, the entire category of spectra is just generated by the sphere. And then you might guess, maybe in motivic homotopy theory, everything is generated by the bigraded spheres. But that's actually not right. So there's somehow much more things. It's like in some sense, sort of an elliptic curve is strictly not built out of its points somehow, for example. But sometimes you want to only think about the spheres, and then you call it so-called cellular spectra. So you have this cellular motivic spectra. So this is what the cellular in my title refers to. So this is the localizing subcategory. So it's generated under colimits and, well, I guess only colimits if I do it like this. Localizing subcategory of SH of S generated by the bigraded spheres. Right, so this is some other symmetric monoidal, presentable, stable, whatever you want, all the good attributes category. And it happens to be, you only allow those things which are built out of spheres, like projective spaces maybe. But not something big like an elliptic curve. All right, and then there's one more property with, or one more construction, which I'm going to use. And this is so-called a p-adic localization or L-adic localization. And I mean, actually, it's basically the same thing as in ordinary spectra. So if E, I'm not even going to say that E is a motivic spectrum or an ordinary spectrum, is completely irrelevant, but then there's something called its p-adic completion, and it's just going to be the homotopy inverse limit of the cofibers of multiplication by p to the n. For all n, there's a canonical inverse system with these entries, which one can form. And the inverse limit is called the p-adic completion. And this is a very well-known procedure in homotopy theory. So I'm sure like essentially everyone knows what this is, but just so we agree that this is going to be the notation. And if you've not seen this, then, well, it's this. Be my guest to think about what that's supposed to do. Okay, so now with all the stupid things out of the way, yeah, I think we have all the things that I need in order to state the main result. So, okay, maybe we use a new page. So the main result goes like this. So I'm going to call it theorem 1. So there's going to be another theorem 2, but it's more like the one is the main theorem and the other thing is a lemma if you want, but I don't know. Somehow I call them theorem 1 and theorem 2. And of course, it's due to me and Paul Arne. And it goes like this. So you take E in SH of Z1/2. I guess that does not come as a big surprise given the title. And I'm going to want it to be cellular. So it's one of these special spectra which can be built out of spheres. And then the claim is that then you can try to work out what this E thing is if you evaluate it on Z1/2. And you can work it out in terms of other things which are maybe easier. So then there is a canonical, let's say Cartesian or bicartesian or pullback, yeah, let's say bicartesian square. And so the entries are, well, you want E of Z1/2. And now I'm going to not quite be able to figure out all of it, but I'm going to two-adically complete this. Okay, so remember, this is a usual spectrum in the most ordinary sense. And I'm going to give you 3 others, and then you get a commutative diagram, which will be a Cartesian square. And the other thing which you put is you take E and evaluate it on the reals, or you take it on the complex numbers, or you do it over the field with 3 elements. Okay, and it turns out that there's a diagram like this, and this is bicartesian. So let me point out straight away that there are like obvious maps like this, because I mean there are maps of schemes sort of in the other direction, or rather because there are maps of rings exactly like this, right? There's not an obvious map here, but it's also not a big mystery. It comes from some sort of rigidity thing where you do a Henselian ring. I'm going to talk about it a little bit more a little bit later. But for now, I mean, the claim is that there's maybe an interesting map here, which you can use to make this entire diagram commutative, and then that diagram will be a pullback square in spectra. And then, of course, you get yourself a long exact sequence from the homotopy groups of this and this and this, and also this. And then you can try to play your usual games to work out things here. So that's the result. Okay, so I hope that makes sense. Of course, this may be not super interesting as it sounds, because, well, who knows what cellular motivic spectra are. So let me give you a few examples of E's which you can stick in there. Like this. Okay, so there are various motivic spectra. How am I going to write this? Here like this. Okay, motivic spectra. Oops. And then, okay, so they will have some name, and then they will represent some theory, which means that if you stick in some ring or some scheme, then you will get out something which you were maybe interested in. So this is going to be representing. Okay, so which ones can I use? Well, one which I can use is HZ, a so-called motivic Algebraic spectrum, and this represents so-called higher Chow groups. Okay, and then there's another one which is called KGL, and this represents algebraic K-theory. I guess in general it represents homotopy algebraic K-theory, but everything I wrote here is regular, right? So then doesn't, in that case, there's no difference. Okay, you can do something else. There's a spectrum called capital KO and represents Hermitian K-theory. What else do we have? Yes, so we have something. Maybe these are sort of the most common ones to think about. Then, but there are some other spectra which are maybe of a more motivic origin. So there's one thing which is called MGL, and that this represents algebraic cobordism. So let me put a little question mark here, because I mean, I would say it represents algebraic cobordism by definition, but I mean, some other people maybe have other definitions of algebraic cobordism, which we may or may not agree with whatever this guy is. In some degrees, maybe not, but I mean, I think he's a pretty reasonable guy. So probably it agrees with all the other reasonable definitions, but I don't know. So then we can get more fancy. There's something called HZ tilde. So this represents something called generalized motivic cohomology. So this is okay, so if you know about this, you're allowed to stick it in. If you don't, then probably you don't care very much. And then there's some other guys, so little KGL and little KO. These are so-called connective algebraic K-theory and connective Hermitian K-theory, in some motivic version of connective. So it's not just taking the truncations. That's something genuinely interesting. And actually, I have no idea sort of how to say anything intelligent about what these guys represent, except that, I mean, for some values which you stick in, it's going to be the same thing as these by definition, but then there's some new values, and I don't know what they are. But in any case, all of these guys, I claim, are cellular in this relevant category. So they are cellular in SH of Z1/2 after localizing at 2. Yeah. And this is not particularly obvious. I mean, there are many results in literature which prove that one spectrum or another is cellular. So I guess MGL is quite easy. And all the other, well, maybe KO and KGL are also reasonably doable, and all the other ones are pretty hard. Yeah, I think so. Yeah. So in any case, so you can stick in all of these theories, and then you can try to use this to, if you know what these things do over fields, then you can try to work out what they do over Z1/2. Of course, there's at least one other cellular spectrum which you knew, and it's obvious or easy that connective covers preserve cellularity. No, not at all, I think. So one can prove it in this case, but I do not know an easy argument for that.
So is this result specialized to KGL and KO, or does it hold in general, even though it's not obvious?
So I don't think it holds in, well, I don't want to make a claim, but I do not know a general argument. So it's specialized for these particular guys. So you can prove it for little KGL by relating it to MG as a quotient of MGL, but even that's not obvious. And you can do it for little KO by some other crazy stuff, basically by looking at the Ada periodic and Ada complete setting. And I don't know any easy arguments for this. Okay, but what I was going to say is that even if you've never heard of any of these guys, you knew one cellular spectrum, and that's the sphere, right? So can we apply it to the sphere? And I mean, the answer is, of course, I'm allowed to do that, but then what can you figure out? So here is another example, which is you can try to figure out the fundamental sort of pi zero of the sphere. And so the thing is that you, over a field, this was done by Morel. So recall the theorem of Morel, which says that if you do pi 0, 0, right? So the homotopy groups are also bigraded, just like the spheres. And you put in the sphere over some field K, what you get is the so-called Grothendieck-Wittring of that field. Okay, so this is the so-called Grothendieck-Wittring. So I guess it's the Grothendieck group associated with the semi-ring. I mean, so the with the semi-group of symmetric bilinear forms on finite dimensional K vector spaces, and then this happens to have a ring structure, and that's what it is. And then you can work out, for example, I mean, for the complex numbers, this is Z, and for the real numbers, it's Z plus Z, and for other fields, it's some complicated thing. It is what it is. People have studied this a lot, and it's a very cool fact that this somehow occurs naturally. Yeah, so look at this definition which I gave, right? You do all of these formal things, and you get out the Grothendieck-Wittring. I think that's pretty amazing. But in any case, so you can do this. And now you would think, what if I stick in something else, right? So the most natural guess, of course, is that you want to get something like the Grothendieck-Witt group of that thing that you stick in. Now, there are some reasons why this is pretty unlikely to be true, having to do with somehow the fact that, yeah, somehow maybe if you have a local ring, then you would think this is a plausible thing to guess. And for a higher dimensional thing, maybe not so much, if you know about how the descent works. But even for a local ring in mixed characteristic, this is not known, as far as I know. No, I don't think that is known. In any case, the point is, of course, for Z1/2, what you think you should get is the Grothendieck-Wittring of Z1/2, right? And well, I don't really know how to prove that, but what I can do is I can stick it into this sequence here, and then I can try to work out the two-adic completion, more or less, of that guy. And I mean, there's some problems, of course, because there can be sort of terms at the left and at the right, maybe, of your long exact sequence, but you can analyze enough things to figure out that this is not a problem. And actually, it turns out that if you put here sort of the Grothendieck ring of F3 and of R and of C, you two-adically completed, and you just take the pullback, then you get the Grothendieck ring here two-adically completed. So what this is going to tell you is that the two-adic completion is what you want. But also, in fact, you can work out what happens sort of rationally, because then by work of, I suppose, Morel and Szysinski-de-Vries, we can relate things to algebraic, rational algebraic K-theory, and to somehow to the real spectra of these guys. So you can work out everything somehow rationally, at least sort of in weight 0. And there you also find the expected answer. And so the conclusion then is that so the conclusion is that one can prove that you get the expected answer too locally. So application of square is that if you do pi 0, 0 of the sphere over z1/2, and if you now localize that too, what you get is the Grothendieck ring of z1/2 localized at 2. Okay, so I feel like this is not a particularly surprising result. Surely this is, if all is right in the world, this is what should happen. I mean, if all is right in the world, I can erase this and it must still be true, but well, it's not really an argument, right? And well, so this is an argument.
Wait, sorry, I'm a bit confused. So you said we should not expect it for the Dedekind domains, but we do expect for Z1/2.
Well, I mean, I'm not sure what to say. So the problem, of course, is that there's going to be a descent spectrum. So I would think that maybe the lowest sheaf should be somehow the sheaf of Grothendieck rings. And then there would be some sort of descent spectral sequence, and you would think that the higher homotopy groups could somehow mess things up. And I'm not quite sure why this does not happen over Z1/2. And I'm not sure that I believe that this should never happen over other Dedekind domains. But yeah, that's why I would say it's not totally clear, but it seems pretty reasonable.
Okay, then the answer to Jay's question is no, it's not known to.
I mean, I suspect that we can cook up examples sort of at equal characteristic for some positive dimensional thing by somehow analyzing this the descent spectral sequence and just showing that there's some contribution coming from pi 1, which messes up. So I don't know a specific example, but I believe it's probably possible to prove this is wrong and sort of for boring reasons in some cases. Okay, so that was my overview of what the result is. And now I'm gonna try and do two things. I'm first going to tell you sort of a moral reason why this should work, maybe, which may or may not be helpful. And then I will basically tell you actually why it's true. I mean, that's sort of the same reason. But the point is that I can give you essentially I can give you a complete sketch of the proof. This whole thing is not particularly difficult, which I guess is why I'm spending so much time on the applications and that sort of thing, because I think the result is quite interesting, even if it's not that difficult to prove. Okay, so why is this true? Right. So there's the rough reason is the following. Roughly is that there are push-out squares so they're going to look like this. You take, let's say, f of c goes to f of r, goes to f of f3, goes to f of z1/2, where for f you take various functors, right? Where f equals one of the following, you take the etale homotopy type, or you take the real etale homotopy type, or I guess I want to say you take the Zariski homotopy type. And then you sort of cohomologically localize this. So as I said, this is supposed to be a moral reason, so maybe let's not worry too much what this is exactly supposed to mean, but I want to show you by example what happens, right? So to look at the etale homotopy types, if you know about these things, etale homotopy types. All right, so what does that sort of thing do? Well, it takes a scheme and it spits out some pro space. And so for C, it turns out that, well, this is pretty reasonable, right? You get the base point. And for R, it turns out that you get RP infinity. Because the Galois group, more or less because the Galois group of R is Z mod 2, and that's B Z mod 2. And then F3 is a finite field, so the Galois group is Z hat, and then that corresponds somehow to S1. Okay, and then whatever you get here, well, so let me write Z1 half at, and one can show that this is going to be the wedge sum of these two spaces. So that's not, I'm not claiming that that is obvious. It's a result, maybe due to Dwyer-Friedlander. So then you can do similar things where you look at the real etale homotopy type. So basically what I'm suggesting here is you look at the set of orderings of your fields. So what's going to happen? Well, C has no orderings and neither does F3, right? On the other hand, R has a unique ordering. So you get the 1 point here. And Z1 half has also unique ordering. So you get 1 point here. Okay, another push out square, how lucky. And then you look at the Zariski. And here, so I'm just basically saying you look at the sort of sets of connected components of your topological space. And what happens? Well, actually everything has a unique connected component, right? So you just get this. Okay, and all of these are push outs, and somehow this, when you look at the proof, this is basically why it works. Okay, but I guess if I give you this moral reason, then you're clearly going to say, well, surely there are other rings or schemes where you can work out all of these things, and surely this sort of, right? I mean, maybe the etale homotopy type is the most difficult one to work out, and surely you can, I mean, maybe you can do it in more interesting or other cases, and maybe then you're equally lucky that in some of them you get similar results on the real etale and Zariski homotopy types. And then maybe the result should be true more generally, right? And the answer is that works, right? So the remark which I want to make is that, so let me say hence, but I mean, of course I haven't proved anything, so it doesn't really make sense. But there are many similar squares. So for example, you can replace this Z1 half, of course, is the guy which you want to replace, right? And then you stick in whatever fields you need to make it work. So for example, you can take something like Z1 over L, and you now need to assume that L is a regular prime. L and, well, odd, of course, because L equals 2 we already did, and regular prime. Right, which apparently means that the class number, well, I mean, that's what shows up in the proof, and apparently that's called regular, which is the class number of the cyclotomic field where you join this as cyclotomic root of unity, this Lth root of unity should not be divisible by L. And apparently there are lots of those, but also there are lots which are not. So okay. There was a question in the chat, which is what about the Nisnevich homotopy type? And the answer is, yeah, that would seem like a reasonable thing also to consider. I guess somehow at this level of talking purely about moral stuff, there's no difference between the Nisnevich and the Zariski homotopy types. And probably there's actually a legitimate statement which one can make, but that this does not make a difference. Right. Okay. So there are many other examples, and in the paper, we give many other. I mean, we state the other results also, but today I'm going to focus on the Z1 half case because basically the proofs for the other rings are basically the same. And of course, we give like a general recipe, like you have the following sort of square of rings, and the following conditions are satisfied, and then it works, and we just check it in many cases. Is the induced map from GW of 3 to GW of C the dimension homomorphism? Yes. Yes, it is. Okay, so now it's time to get, so something which I wanted to say earlier, but somehow this is the natural place. which is that we did not come up sort of with this out of nowhere. So similar squares have been studied by many people. So the initiating result is due to Dwyer and Friedlander.
Sorry,
Yes.
can I ask? So is this F3 random? Like, could you take any FP, or there's
You cannot just take, you cannot take any FP, but I mean, there's some congruence condition. So there are infinitely many possibilities. Yeah, I do not remember the exact condition.
okay?
Maybe it's that 2 should not be a square in that field, but I mean, something like that.
Thank you.
Yeah, I think that's maybe it, but one can write down explicit condition. So
Is
they
it
did this.
congruent to 3 mod 4? Just for the Grothendieck-Witt to work out to be isomorphic.
Well, I will trust you. It's probably right, but I mean, it's something like that. Okay, so they did this in 2 papers in 83 and 94. And basically what they did is they did other things as well, as in sort of, I guess, invent the idea of this kind of localization and etale homotopy types. But basically what they prove is this result where you take E to be either etale cohomology or you take etale K-theory. Yeah, I guess I could have added these spectra. So there are motivic spectra representing these things, and they are also cellular. And I could have added them to the list in the beginning, but I guess I forgot. So these are spectra which by our result you're allowed to use, but they prove this result without mentioning motivic commutative theory at all. And then yeah, so then there's the case of KGL was done by Hodgkins and Paul Arne. Hodgkin, something like that.
And these etale cohomology theories don't follow from the pullback of etale homotopy types?
Sure, they proved there's pullback of etale homotopy types, yeah.
I mean, that's straightforward from the...
Well, these statements are essentially by definition equivalent, yeah. So Hodgkins Østvær, they do E equals KGL. This was in 2003, apparently. They do E equals KGL. And what is it? Eric Karoubi Østvær. So you see Paul Arne has been involved in this for a bit. In when? I did not write up when, but so they did E equals KO. Right, so they established this square for Hermitian K-theory. Okay, so that was my little, thank you very much, Dennis, 2011. Okay, so that was the little history that I prepared. Okay, so we have lots of time. So let me try and give you an idea how this result is proved. So first, of course, I need to explain to you what this map does. So let's call this something like the mystery map. So it's not so mysterious at all. So the point is, how did we get this bottom map, right? Also, which the question was about, it's not obvious what it is, even sort of once you stick in your values, right? So how to get E of F3 twoidically completed mapping to E of C, twoidically completed. And the answer is in the following result. So this is maybe theorem 2. So it goes like this. So let E be a spectrum, motivic spectrum. In the following ring, you take Z, you localize at 3, and then you Henselize that thing, which is the same as taking the subring of the complex numbers of all those elements which are algebraic over Z localized at 3. So they satisfy an algebraic equation with the coefficients integers where you invert all the numbers except for 3. And I mean, of course, you can already guess that there's going to be a generalization, but let me state this. Okay, so this in here be cellular. And then the map from this, it pulls back to E of F3, of course. And then this is going to be an equivalence. All right. So let me say what I said before. Obviously, there's a more general statement. For Henselian local rings. Henselian local rings. But you need some assumptions on them. So I'm going to need to, I don't know if they're necessary, but sort of with the techniques that we use, you need the following assumption. I need it to be essentially smooth over a Dedekind scheme. And then you need to do this at some prime. You can use you can use something different than 2, but it needs to be invertible in the residue field. Okay, so we have this assumption that you should be invertible in the residue field. This is somehow very common in motivic commutative theory. And I mean, for example, it has to do with maybe resolution of singularities, but it's also related to many other things. And I think some of the people here maybe know more about why this sort of something like algebraic K theory is sensitive to whether your base, the coefficients are invertible or not. So that's pretty clear. And another assumption which is sort of pervasive in what we do is that you need to be essentially smooth over a Dedekind scheme. And this has to do with the fact that over Dedekind schemes, Spitzweg has constructed something called the motivic cohomology spectrum, which represents higher Chow groups. But the point is that in this situation, we can somehow compute what this does. And in the end, basically, this result is going to be proved by a computation. We reduce it to something where you have groups on both sides. You just check an isomorphism by computing both sides. And so that's basically where this comes from. So this essentially smooth over Dedekind scheme assumption is always going to mean that I'm computing something using homology in a non-trivial way.
But without the smoothness assumption is not going to be quite correct, right? Because homotopic K theory, for example, doesn't have rigidity in all degrees.
Right, but I mean, you could be a regular ring, for example, which does not admit essentially smooth map to a Dedekind domain, and then maybe it's true. I don't know, but I can't prove it like this. And I mean, I can't prove it at all. I don't know how to do that. But you're right; it can't be true in complete generality. Okay, so now what's the point of theorem 2? I think you've already puzzled it out, but it means that I can, of course, rewrite my square in a way that is looks more natural. So, i.e., there's a non-mystery square or diagram. And it goes like this. You take E of Z1/2. And then you go to E of R. And then you go to E of this Henselian local ring, which, as I said, embeds into C. So now there's an obvious map to E of C, like this. And then you further pull back to E of F3. And then you don't forget to complete everything. And then this map here is an equivalence. And so it's enough to prove that this thing here is bi-Cartesian. So that looks maybe more reasonable. And I mean, this also shows that, I mean, it's completely natural in E. I mean, this extremely canonical, this diagram.
Sorry, so this vertical isomorphism works only after you two complete?
Sorry, the rigidity thing?
Yeah.
Or yes, I think that's also necessary. Yeah. Clearly, there are counterexamples if you do not complete. Yeah.
And the right-hand side you should also complete.
I should definitely complete. Sorry. Yes.
Okay.
Thanks.
And then there is a question from Dennis. Thank you.
That's a good question. I do think it depends on embedding. So I think, I mean, I described it as a subring of C in a canonical way. So in a sense, there is a canonical embedding, but I think if you change it by an automorphism, you will change the map in general. Yes. I think. Okay, so now we actually know what the statement properly is. So now how do we prove it? Yeah, so I have another 20 minutes. I'm probably going to be done in like 10. So kind of coffee early, but so how do you prove this? Okay. And well, as I said, we're going to do a bunch of reductions, which eventually bring us to something where we just compute both sides and you see that it works. And in some sense, I think this is a bit of an unsatisfying theorem because, I don't know, just compute both sides and it's the same. But I guess the techniques themselves, they're, well, in some sense, they're well known, in particular, sort of the classical homotopic analogs. But I think they're also, yeah, I mean, the techniques are fine. So we use the following reduction techniques. So one is that the way the motivic categories are set up, these sphere spectra, they're always compact. And so what this means is that basically this diagram that we're trying to prove is a Cartesian square. It's going to be, I mean, it depends on E in a fashion which preserves colimits. And what this means is, of course, that if you prove it, I mean, you want to prove it for the entire localizing subcategory, it means you only have to prove it for the generators. Okay. So to prove theorem for all cellular objects or spectra suffices to prove the case E equals, well, one of these cells, sigma PQ1. All right, so that's the technique one. So I can prove it for the sphere, basically. The second is that you use the so-called eta complete fracture square. So eta is the so-called motivic stable Hopf map, and it goes from sigma 1, 1 of 1 goes to 1 is the so-called motivic stable. Yeah, so the motivic stable Hopf map. Very interesting map, maybe a subject of a bunch of other talks. Not this one, but so it's going to show up for some reason. And so the fracture square looks like this. You take any spectrum here, and I mean any motivic spectrum, and you can build it as a Cartesian square like this. You invert eta, or you complete at eta, or you do both. Of course, you have to do it in the right order because otherwise you get 0. So there's only one reasonable order. And this is going to be Cartesian, by Cartesian, whatever. And so what that means is that I can assume either that my guy is eta complete or eta periodic. Okay, and then the final technique which I'm going to use is these sort of nilpotent resolutions. And it goes like this. So if E in SH of S is connective, so I mean it's maybe not immediately clear what that is supposed to mean, but the spheres are going to be, I mean, maybe n connective for some n. That's basically all that we need to know. Then if you complete your guy at 2 and at eta, right? So I mean, we are always completing at 2, and also we said we can complete at eta or invert eta, but let's say we do the completed case first. Then you can build this in a specific way, which is, I mean, your usual Adams tower type thing. So I'm doing the limit of E smashed H z mod 2 tensor n plus 1, and I guess n in data. So it's a totalization. I mean, yes, it's the totalization of the obvious thing that you do. And similarly, if I take E, sorry, what's that question?
Where's eta on the right?
there's no eta on the right, but I mean, what happens is that pi 0 of hz mod 2 is sort of pi 0 of the sphere modulo 2 and eta. And that's why the 2 and eta are here.
Mm.
You don't look very happy.
No, but it's okay. Thank you.
Okay. And the other thing is if you invert eta, then what you obtain is, well, you can obtain it as follows. You take another limit. Basically, you resolve with respect to a different spectrum. Limit over n in delta of E smash HW to n plus 1. Okay, so maybe hz mod 2, that's a reasonable guy. That's the motivic cohomology spectrum. We sort of know this, right? So let's say we pretend we know this. This is motivic cohomology spectrum. And I said before, by work of split spec, we can compute this in reasonable cases. So this HW thing is the so-called, well, I'm going to call it eta periodic with cohomology spectrum. Okay, so you can certainly always get a map like this. And the fact that these maps are equivalences is actually not that trivial. So, I mean, there's of course sort of a general theory of nilpotent resolutions in presence of a T structure and so on and so forth. That's easy. But you want to know that these spectra actually satisfy the required assumptions on them, right? So, I mean, as I claimed, and as I said to Mura, that the pi 0 of this thing is pi 0 of the sphere spectrum modulo 2 and eta. And this is actually not that obvious because the T structure which we use is something called the homotopy T structure, but the hard is not really explicitly, I mean, we cannot really describe the hard explicitly unless the base is a field. And so you need to give some rather abstract arguments. And even if I allow myself to be very abstract, I do not know any easy arguments. So in order to know that this works, you need to, for here, you need the Hopkins-Morel isomorphism. And for here, you need to basically study the eta periodic category quite carefully, I think. So, I mean, this uses rather non-trivial input. So maybe Hopkins-Morel OUR ISO plus study of eta periodic category. By which I mean paper of me and Hopkins. Okay, but once you have these inputs, you get quite formally that you can use these resolutions. And now, if you combine all of these, right? So okay, so I need only prove it for the sphere. Then I can do this fracture square, and I can again approximate this guy's eta periodic, right? So I approximate it by eta periodic spheres. So basically, you need only prove it for the eta periodic or eta complete sphere. And then I do this resolution here, and it basically tells me that you only need to prove it for these guys, right? Because E is more or less the sphere. But then again, you can approximate them by spheres and so on and so forth. So basically, you only need to prove it for this guy and for this guy. Okay, so the upshot is suffices to treat E equals HW or E equals HZ mod 2. Okay, and then basically the answer is that you know exactly what all the homotopy groups are. I mean, over all the relevant rings. And I mean, this guy here is related to etale cohomology, so you need to compute some things. It's maybe not totally trivial, but people have computed etale cohomology for a long time. And here you can just write it down explicitly, and then, well, you check that the square which you get is Cartesian. So I have some minutes, so let me show you by example how this goes for HW. Right? Okay, so the summary is now just compute. Okay, so e.g. E equals HW, and then, well, over any, well, I guess over any of one of the rings which are relevant for us, you can work out pi star star HW, right? So it's going to be some bi-graded thing, but of course the 1 degree is sort of stupid because you're eta periodic, And it turns out that the other degree is also not that interesting. So what you get is which ring of your base with eta plus minus 1. But again, not for all s. So if either s is Henselian local, oops, essentially smooth. Or let me just say, yeah, so we only care about this case, Henselian local and regular of dimension 1. Or if S is an open subscheme of C1/2. Or, yeah. Okay, and this somehow has to do that in this case, with the fact that in this case, the Witch ring has no. So this is what I said before, is that even for general Dedekind rings, I don't know if this is true, but C1/2 somehow some special things happen, and then it's okay. So now what you need to prove? Well, for theorem 2, what you need is that basically Witch ring of Z3 Henselized should be the same thing as the Witch ring of F3. Or I mean, more generally, maybe you want to know that if you take Henselian local ring, then the Witch ring of the, maybe of characteristic not 2, then the Witch ring of the ring is the same as the Witch ring of the residue field. And that's, I mean, I don't know who proved this. I know a reference about this result due to Jeremy Jacobson. In any case, someone else has done this, and this is correct. So let me say Jacobson. Oops. And he proves that this works. And for the other square, you need to work out the Witch rings of the other rings, of course. Yeah, and so you work out the other things. And for theorem 1, so what we need is that if you take the Witch ring of Z1/2, and then you go to the Witch ring of R, or the Witch ring of F3, or the Witch ring of C, then this is the square of abelian groups, which you want to be sort of Cartesian if you look at the associated Eilenberg-MacLane spectra. So in other words, you want this square to be bicartesian. So I guess Cartesian, and this sum here is surjective or something like that. We need this to be bicartesian. Okay. And so I guess, I mean, I will use 1 minute to tell you what all of these rings are, and then you can check that it works, right? So you work out that this thing here, I mean, okay, so these are very well known. This is Z mod 2, and this is Z. And so the other ones, I mean, also find them in any book, I'm sure. So we can work them out. So, or I mean, I can tell you what the answer is. The Witch ring of Z1/2 is going to consist of, you take Z and you adjoin basically the class corresponding to 2. And then there's going to be a relation, which is that, yeah, so twice 2 minus 1 equals 0. So somehow you have this 2-torsion class here, and well, there's some elementary property about symmetric bilinear forms, which is very easy. And I guess 2 squared is equal to 1. And so it tells you that basically it's going to be a Z and a Z mod 2. Yeah, so this is Z plus Z mod 2 on this guy. And if you go to F3, you basically get the same answer, except that 2 is now the same thing as -1, and angle brackets -1 is the same thing as -1 in the Witch ring, right? So this is basically the same thing, modulo 2 equals -1, and so then what you find is that this is Z mod 4. Yeah, twice -2 is equal to 0. So yeah, that works out. So this works out to be Zeeman 4. And then, yeah, now you stick all the things in and you stick all the maps in and voila, it works. Okay, so that's the end of, well, I mean, this is like half of the proof, half of the last thing which you need to check. You can do something similar with etale cohomology. As I said, the computation is a bit more difficult because, but I don't know, maybe it's not. I guess I just know how to look up these groups. Yeah, okay, I guess it's a bit more difficult because there are more groups, so you need to check more, but it's all not a big deal. Okay, so that's all I had prepared.
Thank you very much. That's fun. Are there questions?
So could I ask, do you have a pullback square of categories?
So we thought about this, and I suspect that the answer is no. So what's going to happen is that, yeah, so you do this sort of thing, SH of Z1/2, let's say two-additively completed, and it maps to the fiber product of and then you need, well, for this to be plausible by what I said, you should have cellular everywhere. And you would ask if that is an equivalence. And I mean, what I said is, I think, essentially equivalent to saying that this is fully faithful. And I mean, for a while, I thought that I could prove that it's also essentially surjective, but eventually I failed. So I suspect that this is not essentially surjective, but I'm not like 100% sure.
How do you define the map from SHF3 to SHC? Because rigidity tells you only a fully faithfulness statement again, right?
Well, but this is going to be essentially surjective, essentially by definition, because you have the same generator.
Oh, because they're cellular. Yeah. Thank you.
Yeah. So that's right. You use rigidity to replace this by the Henselian ring, and then you actually have the maps. But then still, it's not obvious that sort of. Yeah, I do not know how to prove essential surjectivity, and my suspicion by now is that it's maybe false.
Thanks.
Sure.
So I guess,
Sorry, one person at a time, please.
I'll go, Kristen.
Do you have comments about the completion and maybe removing it?
I don't think I do. So I guess my gut feeling is that in general, this is not really reasonable sort of in the uncompleted situation, because also sort of rigidity is not reasonable in the uncompleted situation. On the other hand, I think that, I mean, in some examples like K-theory, I think it also happens to somehow work maybe only too locally and not too completely. But I'm not sure that I know a pattern why this is. So there's, I mean, again, you check the rational part and it happens to work, but I'm not sure that I have an argument for why this should work more generally. So unfortunately, the answer is
you mentioned the results of Spitzvec on pi naught of the sphere over a Dedekind ring. Mm-hmm. Those are uncompleted, right?
You mean the result in the beginning about the growth in the grid group? Or
yeah, yes, that's what I meant.
Yeah, yes. So that's another example of, I mean, I know the sort of two completed part because of this particular argument, and then I look at the rational part and I do a different argument, and it happens to again assemble in the right way. But what I'm saying is that I do not know if this is just sort of luck, or if there's an underlying pattern which one could prove for some class of spectra.
Great, thanks.
I'll go. So I think you could get a complete computation for MGL or any of the truncated Brown-Peterson spectra of Z adjoin 1/2 from this result. Have you worked out those details? is it something that's kind of presentable?
So I have definitely not worked out these details. So I agree that you should be able to certainly work out much more. Yeah, yes. So I mean, I think the only reason I will answer is that you're right. There are many things that one can compute. So certainly, I mean, even for just the sphere, you can compute more than what I told you. But I have not done it, and I mean, maybe it's not the biggest secret that I'm not a very great computer. So yeah, so definitely there are many opportunities for things to try there. I don't know how reasonable the answers are going to be, but probably not super terrible if the constituent components are not super terrible. So should be doable.
Are there more questions? If not, let's thank Tom. And I'll stop recording and then you can ask your actual questions.